Right, everyone, we've dwindled in numbers, which is a shame, because this is one of my very favorite topics. And this is one of the things I think, if I sort of can think back a very long time now, when I was at school, we started learning about sort of physical geography and how landscapes formed. And this sort of really sort of made me realize all of a sudden that this whole other layer to the landscape that you don't necessarily see if you don't know about it. So today we're really going to talk about the landscapes left behind by ice. Because today we're still in an ice age, there's still ice on our planet, but there's a lot less than there has been in the past, and so a lot of the landscapes we see have really been shaped by the movement of ice. So first of all, I want to get a quick assessment. Who has been up to the Sierra Nevada mountains at some point in their life? Who hasn't been up to the Sierra Nevada? Let's do the other way around. Oh my goodness, what have you guys been doing? People come from all over the world to go here, to go to Yosemite, to go to Sequoia. So hopefully today will inspire you to go. And for those of you that have already been, hopefully this will allow you to see that landscape in a very different way. Okay? So, oh, hang on, I should have said, does anyone recognize this?
Half Dome.
It's Half Dome. It's in Yosemite, and that's my photo. So you can get these, and you don't have to be a professional to do this. So, ice has enormous power, okay? Ice has enormous power, and it really is able to sculpt and carve and erode away huge amounts of rock. And so often where we find glaciers, then we see that they've really shaped the landscape around them. And they do transport sediment in very specific ways that we can sort of track through the world, but also they transport it a really long way often. And those patterns of what we call glacials, like full ice ages, like maybe 20,000 years ago, when we had our big ice sheets over North America and Europe, and interglacials, so more like today, where we only have a couple of ice sheets around. Those patterns have really shaped the Sierra Nevada mountains, for example, the other mountain ranges around, and definitely high latitudes. So, let's get started. I want to see what you know. So, tell me, which of these is not a glacial landscape? Which of these was not formed in some way by the movement of ice? Okay, any last votes? Right, let's take a look and see what people think. And you know what? Anyone would think I knew what I was doing, because I'm going to ask you exactly the same question at the end of today. If I still get that, I'm going to be horribly sad and cry, okay? So pay attention, and I'll ask you again at the end, and we'll see if people can work it out. Okay, so what do glacial landscapes look like? This is something that you would associate with glacial landscapes. They're really stunning, sort of dramatic images, and that's because glacial erosion produces these really dramatic landscapes. It really sort of produces very steep and deep-sided valleys. It produces really pointed spires and ridges. And so that's sort of our sign that there's ice in the landscape. And is it actually ice that is doing the work? Is it actually ice that is sort of moving past and carving it out? Probably not, because you're reading ahead. But why is ice actually not responsible for forcing things aside? Yeah.
So they slide on water, the glaciers?
They slide on water, but also, I mean, if it runs into a barrier, what happens? It melts. Do you remember we said that if it runs into a barrier, that extra pressure, it doesn't, so the ice doesn't necessarily, or sometimes it can, but often it's not forcing its way past the barrier. What's happening is that extra pressure is melting, and so that water is moving around the edge. And we'll see specific landforms today that form as a result of that. So the key thing is, it isn't the ice that's sort of really sort of driving that erosion. It's what's carried within the ice. It's things like sort of grains of sediment. It's rocks that are carried in that lowest part of the ice. And they act just like sandpaper. They basically scrape against the bottom of the valley, against the edges of the valley. And so that's how you erode. Okay? And so we're going to go back a couple of weeks now to these little videos that I showed you a while ago, but now let's think of them a little bit differently. So, first of all, this video was the one that everyone left for. I'm not going to play the sound, and I just want to show you something. So they've tunneled into this gigantic glacier, and you can see, in particular, there's nice pure glacial ice above, but as you get close to the rock bottom there, you can see all of that sediment incorporated into the ice. Okay? So you can see that really nice distinction between that sort of top ice with no sediment and then that sort of meter or so above the rock with lots and lots of sediment. And I encourage you to watch that video again if you didn't. And so you can see there's everything from little tiny bits of dust to quite big rocks, as she sort of shows you there. Okay? Why is that important? Because, do you remember this video that I showed you? Okay? So now look at the base of that ice. You can see that there's really irregular bumps. That's not necessarily the ice itself. That's bits of rock stuck to the bottom of the glacier. And you can imagine that, okay, we're moving over an air gap now, but as that ice slides over the underlying rock, it's grinding against it constantly. And so it's really, really effective at eroding away. Okay? And so my image here shows the effect of that. Can you see all the lines running down the page? That's what happens as that ice sort of moved down this slope. It had bits of rock in the base of that ice, and as the ice slid down, that rock got dragged against the surface, and it's left behind these striations, we call them, these sort of lines in the rock itself, which is really neat. So next time you're up in Yosemite, in Sequoia, have a look for these. They're everywhere. You can see them on the nice sort of polished surfaces, and they're a wonderful sign, and you'll be able to look at it and impress your friends by telling them which direction the ice was moving in. You're like, do you know there was ice that moved in this direction? And hopefully they'll appreciate it. Not all of them might. Okay. These things also produce what we call rock flour. So if you can imagine that we're constantly grinding rock at the bottom of our ice, then yes, we produce big chunks and little chunks, but we also produce really fine material, really sort of very, very fine dust. We call that rock flour, just like you sort of grind wheat down into a flour. And in particular, what you'll see is that glacial lakes often have this sort of milky, beautiful, sort of green, or even like this turquoise blue appearance. And it's because of that amount of sediment that's in these lakes. Basically, it's scattering the light as it tries to go in. And so often, glacial lakes in these landscapes are beautiful colors. And this is taken from a lake up in Banff National Park, up in the Canadian Rockies. And they're famous for having these beautiful blue lakes due to the rock flour coming in. So what other features do we see as a result of that erosion? So we've learned how glaciers erode, and they produce these striations. And on a big scale, what they do is they basically polish the rock. They scrape away any sediment or soil that was on the top, and they polish it down. And so here you can see that really steep sides that are very characteristic of glacial valleys, and how it's a really sort of pretty smooth rock surface. And that's been polished by that sandpaper action of the glacier moving through. And then we have roches moutonnées, and my French is pretty bad. But those things, you'll notice that a lot of the glacial terms are French or Swiss, because that's where in the Alps they were sort of first finding this stuff out. And these form because of this pressure melting thing. Okay? So you can imagine that my ice, in my diagram on the left there, my ice is flowing along, and then it hits a bump. And do you remember we said to get past that bump, as the pressure builds up on one side, that melts the ice. Okay? So we are getting some sort of abrasion, some sort of sandpapering action on one side, but as it hits that bump, it melts. And then that water will sort of trickle around, and then on the other side, it will refreeze. And as it refreezes, it basically glues those bits of rock into the ice. Okay, so if you can imagine sort of bits of water trickling down into those cracks, when it refreezes, it becomes part of the ice, and so it gets pulled away from the rock formation. It's what we call plucking. Does that make sense? Yeah? So melting on this side, refreezing on that side, and as it refreezes, it pulls away bits of rock from the mountain. And so what we get left with are these really asymmetrical hills. So you can see that this is sort of an example. You can see that that rock in the image there is really quite gently sloping on one side, and then it's much steeper on the other. And it's because of this process. So we're getting gentle sort of sandpaper action on one side, and then on the other side it's much steeper because things are being plucked away. So here is an amazing example, again from up near Yosemite, and it shows a roche moutonné. And so what I want you to tell me is, which way was the glacier flowing? Was it left to right or right to left across my image? Any last answers? Oh, you know I'm not going to accept that today. Talk to your neighbor, find out if they were right and you were wrong, or tell them that they were wrong and you were right. And I'm going to ask again. Okay, so tell me, what do you think? Last few seconds? Right, let's see if we get a better answer. Not a lot, but it'll do. So the majority are, in this case, they are right, okay? So think about what I was showing you just before. There's one gentle slope and one really steep slope, okay? So here, you see you've got one gentle slope up here and then one much steeper slope. So on this side, that ice is sort of moving in this direction, and as it meets that obstacle, some of it is melting and some of it is being sort of squeezed over the top. And so you get abrasion, just that sandpaper action of the rocks at the base there. But then on the other side, you can see that all of a sudden, all of that pressure will be released because it's now got this extra space on the other side. And so that water, that pressure on that sort of water will be released. And so if it's cold enough, it will refreeze. And as it refreezes, it carries rock away. And that forms that much steeper slope. Okay? So right to left in this case. So let's think about what sort of patterns we see. So this is a classic river valley. So things that sort of should leap out at you as a river valley are that it's V-shaped. Okay? So that river at the bottom fits really nicely into that V. It looks like it probably would have carved that valley pretty easily. Okay? It looks about the right size. Okay? The tributary valleys, so the valleys that feed into your main valley, which we often call the trunk valley, they're about the same level. Okay? So those are features that would look of a river valley. And then if you imagine that our climate got much, much colder and we filled a lot of this space with ice instead, you can see that that movement of the ice and the presence of that ice has carved much steeper sides, and it's really sharpened the landscape, and it's really also made everything much deeper as well. As it moves along, it's really powerful at carving down. And so you can imagine what we'll have left if that ice then melts away. We'll have something that looks much more like Yosemite Valley all of a sudden. So we have this really quite straight, steep valley coming down, and it's U-shaped. Instead of being V-shaped, it's now really steep sides and a much flatter base. And you can see that my little stream running through the middle there looks a little bit lost. They're actually called misfit streams because they don't look like they could have done anything to carve this enormous valley down, and they couldn't. It's the ice that's doing it instead. You can also see that where those tributary valleys join in, there's actually now a big difference in height between where those tributary valleys would join and the depth of that main stream. And we call these things hanging valleys. So where that tributary would join and there's this big cliff, we call that a hanging valley, and often they have these little waterfalls coming down. So where you see those waterfalls in Yosemite Valley, if you're high enough up, you can see that actually they are little individual tributary valleys, and what we're seeing is just this sort of big cliff where they join the main valley. We also see that where those glaciers have carved sort of back towards the top of the mountain, especially if there's sort of lots of them around the peak, we have a horn left behind at the end, okay? So if we have really steep sides and lots of glacial valleys around a peak, then that really steep peak is called a horn. And that really sharp looking sort of ridge between two steep glacial valleys we call an arête. Okay, a nice sharp arête. So here's Yosemite Valley again. So having just seen that, hopefully you can now appreciate it. It is this enormous sort of straight, sort of very steep-sided with a flat base. You can see the tiny sort of stream running through the middle that obviously couldn't have carved away this enormous valley. Unfortunately, we can't see one of the waterfalls. It's just off to the right-hand side there, but if you sort of panned around, you could see one of these tributary valleys coming down. So it really does look exactly like the drawing. So, horns. What is the most famous horn? The Matterhorn. Everyone's been to Disney, right, and has seen the Matterhorn. It's a horn, and so this is the Matterhorn. It's a real photo, not the Disney version, but you can see that on all sides, what happened was it was surrounded by glacial valleys. And so what happened was that very top was left out, and so it wasn't eroded away, and so now we just have this really vertical sides to it. And what happens is when we have that peak sort of sticking out above an ice sheet, we call it a nunatak, which I think is one of my favorite things. Nunataks, I don't know. So nunataks, they're these little points that stick out above the ice, and so they tend to not be eroded as much. And now we have our cirques and tarns, and this should sound familiar, that word cirque, because it's one of the types of our glaciers, if you remember. So here's our little cirque glacier, and it's really where that ice first starts to form, in this little hollow in the mountain somewhere. And it's probably in shade for more of the time, and so ice can build up and build up. And as that ice sort of builds up, it sort of erodes down and sort of steepens the back wall and the base of that little bowl, and then it spills out over a ridge down into the valley. And so what happens as you melt that little cirque glacier is you get left behind this little circular pocket on one side of your mountain, and we call that a cirque. And where that ice sort of deepened that little hollow, we often get a little lake in that hollow, which is called a tarn. And again, you see these everywhere up in Yosemite around the Sierra Nevada mountains, these little cirques and tarns. So here's a much nicer photo of that hanging valley where we talked about before. So my main trunk valley is coming down the base here, and you can see how another glacier would have filled this little valley, and it's sort of coming down to join the main one. And it has had as much ice in it, so it hasn't deepened as far down as the main valley has. And often we get this little waterfall left over. And then our last thing, I think, to do with erosion is, well, what happens if we have things like tidewater glaciers, and then we have sea level rise, or that glacier melts back? What we're left with is what we call a fjord. And so we see lots of these up in Alaska. It's originally a Norwegian name, which is why it's spelt funny. And these are just those U-shaped glacial valleys, so there's really steep sides again, flat bases. But now they're flooded with seawater, and they're some of the most spectacular landscapes. And you can see the people stood on top of the rock there for scale. These things are really huge, very, very large scale. So let's think about how our glacier is transporting rock, how it's transporting sediment, because we've said that it's really good at eroding, it's really good at picking up material and carrying it along. So let's look at that in a little bit more detail. So first of all, we said plucking, which is where that ice basically tears away a bit of rock from sort of the bedrock or from the sediment, because it's sort of frozen solid to it. And this happens all the time at the base of the ice as well. Okay? And as that happens, you can imagine it's sort of moving upwards because we have constant ablation and melting at the top. And most of that flow is sort of coming along the bottom. And so those rocks end up moving up through the ice. And then as that glacier gets to the end, as it melts, it's carrying all the sediment. We saw how much sediment was in the base of that ice. As it melts, that sediment just gets dumped in place on the landscape. Okay? And so those fragments move both within the glacier until it gets to the end. But we also carry a lot of sediment just on the top, So the ice doesn't care if a big boulder falls on it. It's still going to be moving. It's still really heavy. It's still flowing. And so here you can see an example from the Himalayas, I think, where we have these big glacial valleys that are really good at eroding. And then we have very unstable slopes around. We have these really big cliffs and steep sides. And so, unsurprisingly, a lot of rock material just falls onto the glacier. And it goes, okay, and it just keeps going. And so that rock is transported by that ice. And really huge chunks of rock, sort of house-sized chunks of rock, can be carried along on top of a glacier. Okay. But it has to go somewhere. So it gets carried along within the glacier. It gets carried along on the top. Okay? And then as it gets to the terminus, the end of the glacier, it melts and it's dumped. And if that end of that glacier is in the same place for quite a long time, then what happens is that all of the sediment piles up in front. Okay? And we call that big pile of sediment a moraine, which is a funny word, M-O-R-A-I-N-E. And if it's at the end of the glacier, we call it a terminal moraine, because it's at the end, terminal moraine. And that's usually the biggest sort of pile of sediment that you see. And what do you think the sediment size might be in here? Do you think we're just going to have sand-sized things, or do you think we're going to have really small and really giant pieces of rock? Everyone's stunned into silence. What do you think might happen at the end of a glacier? If you went to the end of a glacier, do you think you'd find like a beautiful sandy beach type sediment, or do you think you'd find huge chunks and small chunks, things like that? Huge chunks and small chunks, absolutely. It's not very well sorted. We get a whole variety of different material just dumped at the end there. It's very poorly sorted. We also get sort of collections of moraine at the sides and in the middle. And at the sides, they're called lateral moraine. And in the middle, they're called medial moraine. So they're nice and easy to remember. And lateral moraines are, if you imagine that if we're going to have rocks falling onto our glacier, then it's probably going to happen at the sides. And so a lot of the rock that's sitting on top of my glacier is at the sides. And so that's our lateral moraine. But just like rivers can sort of flow into one and sort of carry on, glaciers do that as well. So if you have two valley glaciers and they come together, then each of their lateral moraines suddenly join up. So in the diagram here, you can see that two of the glaciers at the top, they would both have lateral moraines, but as they join together and flow as one larger glacier, that now is right in the middle. Okay? So, and I'm not making it up. This is a real photo showing the same thing in action. And I have another question for you. Thinking about that process I just explained, even if we can't see it on here, how many glaciers are actually joined together to produce this pattern in our ice? So talk about it with your neighbor for a second. Okay, and tell me what you think when you've decided. Any last votes? I think there's a few more people here. Right, let's take a look and see if we agree on this one. Close enough. The number 3 would be right, okay? Because we have two medial moraines, right? So we have two glaciers coming together to form that one medial moraine we see on one side. But what must have happened somewhere that we can't see over on the right-hand side of our picture, in order to get this second medial moraine, two other glaciers must have come together, okay? So actually what we're looking at here is the sort of main stream of ice that's being contributed from sort of at least 3 separate little glaciers coming together. Okay? Does that make sense now for the people that weren't sure? Not seeing any response, so I'm going to go yes. Okay. So these aren't little piles of sediment. This is a pretty big pile of sediment. This is a terminal moraine. This is one that you find down in New Zealand. And so these are really big sort of features that you can see in the landscape. And again, if you go, especially in the eastern Sierra, there are some amazing sort of big moraine piles that you can see. Often, even if you look at satellite images, you can see these left behind. And so what they mark is that sort of furthest point that the ice reached. Because if it was sat there and it was stable for sort of decades, it allowed that moraine pile to build up. And especially now where most of our glaciers are retreating, that ice is now moving away from this big pile of sediment. And so now we can see how far that glacier used to be. We can even see sort of other moraine piles much further down the valley where that ice used to extend, perhaps in the last ice age, which is really neat. Okay, so they're very good at marking the position of that glacier. And it's not just sort of individual glaciers do that, but do you remember that North America used to be covered by a gigantic ice sheet? And how do we know this? How do we know where the edges of it were? Because we can go and we can look where the terminal moraines are. And if you go to the east coast, everything marked in yellow there are sort of terminal moraines that you would be able to find at the surface. So you can picture how big this ice sheet must have been, right? And so you can see how it sort of formed these different generations of terminal moraine, which is very, very neat. So behind that terminal moraine, okay, we often form lakes. And I imagine you can sort of see the reason why, because if we have this big pile of sediment where the glacier sort of marking the edges and the end where the glacier used to be, and we've retreated back from that as the climate has warmed somewhat, and we're melting the ice, then that water is going to run down at the front. And if it can't travel through that moraine, it's going to build up a lake. How stable do you think this lake is? Would you want to build your house downstream from this? Why not? Why do you think it wouldn't be stable? What's it made of? Just loose sediment, right? And so it's not solid rock sort of forming the barriers there. And this is what we're going to spend a lecture talking about. We're going to talk about the risks in a number of places now, especially around the Andes, of what we call glacial outburst floods, okay, where these things give way, and what we can do to try and address the hazards to that as that comes more and more frequent. Okay, so let's see how you do with this one. So which letter on here, A, B, C, or D, marks the furthest extent of the valley glacier that used to fill this valley? So it's not here anymore, but it used to fill this valley. What letter marks the furthest extent of that? So you can consult your neighbor again if you would like. Any more votes? Okay. Once again, I'm not going to accept that. Turn to the person behind you if your friend is giving you dodgy information and see what the person behind you might say. Okay? Okay, so tell me again. Which letter marks the furthest point that the ice used to extend to? Last few votes? Okay, let's see how this went. So we still have a bit of a split, and the majority in this case would not be right, I'm afraid. But the second place answer, it's a game called Spot the Terminal Moraine. Can you spot the terminal moraine? Yes? Here at D, you can see that big pile of sediment there. Oh, yes? Does that make sense now? No? So you can just about see the ice that's left on this side, on the left-hand side. And you can see that the valley is sloping down in that direction. The ice would have moved in this direction. And we've got our tributary valleys. How do we know that they're the tributary valleys? So they're higher up. And so you can see that our sort of glacier would have come down until D. And D marks that terminal moraine there. And it's forming this nice wall. And behind that wall, we have the meltwater coming down, forming a lake. Yes? Sometimes it just takes a bit of practice looking at these landscapes and identifying those features. So don't panic if that's sort of a challenge for you. But it's one of those things that you can go and you can look at these images on sort of Google Earth even, or there's just the Google Maps, and sort of look at these features. So given that this was a bit of a disaster, I want you to actually have a think. And so look back at your notes. Think about the things that we talked about today. All of those different erosional features. And I want you to think about how many of those features we can see on here. Okay? So how many can you spot? So tell me. Oh, other way, back. And if you all say greater than 6, I'm going to make you tell me which. Okay, last few seconds. Great. Okay, let's take a look and see how confident people feel about identifying some of these features. Relatively confident. That's good. Okay. So let's have a look and see which ones we can identify. So would someone like to name me a feature that they spotted on here that's related to glacial landscapes? Yeah.
Moraine.
Moraine, okay. I already gave you that one, so that should have been one of your sort of 5 or 6 at least. So the moraine down there, the terminal moraine. Someone want to give me another one that they spotted? The tarn thing? Yes, absolutely. It's sort of hidden right now by ice, but the cirque, right? Definitely we have the cirques. And how many do we have? We have at least, I don't know, it's difficult to count. On the mountain at the very top, we have at least 2 there. And then we have another 1, 2, potentially 3 there. Perhaps another 4th at the bottom here. So they're everywhere, right? What else did you spot? Arêtes. Can you see those arêtes? Those really sharp ridges running past. Ah, yes. All of those things that I've been telling you. Up here, we can see a beautiful arête. Here's another arête. Here's another arête. What's this? A horn. Okay. What else? Did anyone get any others? The lake. The lake is also a glacial feature, so that proglacial lake. Any others? The hanging valley, absolutely. So we can see where those tributary glaciers are feeding in. Eventually there'll be like a lovely little waterfall as that ice melts there. Those hanging valleys. Anything else? That's pretty good. I'm impressed, guys. Well done. So you can see that all of those things we've talked about are really visible in these images, and at first you don't necessarily spot them. And this is true in the real world as well. It takes practice to do that. But next time you're up in the mountains, then take the time to look around and see what you can spot, because I guarantee you there's so many things up there, and all of a sudden it just exposes this whole other layer to the landscape that you never knew, and you can imagine what it would have been like as the ice was there, which I love. Okay, so deposition. So we talked about erosion and a lot of those features. We talked about moraine. There's also some other depositional features, so sort of depositing sediment that are familiar. And these are what we call erratic boulders. And one of my favorite ever accidental final exam question answers was someone that wanted to call these erotic boulders. They are not erotic. They are definitely erratic boulders. And so why are they erratic? They are erratic because we find them in places where they shouldn't be. They're often hundreds of kilometers away from sort of the nearest sort of type of rock that would sort of produce this boulder, and they've been carried. And also you can imagine that big rock in the middle of the field there. Where could it have come from? What could it possibly have moved it there? And it really is the fact that we had this big block sat on top of ice. And as that ice was sort of moving along, and then it melted and it deposited that boulder in place. And we, again, in our sort of higher latitudes, we can find these everywhere. And they're really neat. You can track from what type of boulder it is. You can work out where it must have come from, and so where the ice was flowing, which is a great tool. We also have what we call kettle lakes. which are really fun things. And especially if you go along to the east coast around that coastline we were just looking at, around Cape Cod, for example, you can see these in the landscape. And what happens here is that as our big ice sheet retreats, or our glacier retreats, then it doesn't sort of melt beautifully evenly across the front of that glacier. We get really big chunks of ice falling off the front. And just like if you have a really big chunk of ice outside, it takes a while to melt. So the bigger the chunk of ice, the longer it takes to melt. And so if you imagine that that sort of ice chunk falls off the front of my glacier in my top left image there, and then we still have melting around, and so we still have deposition of sediment going on around that. And so when that ice finally melts away, what we have left is sediment all around and a big giant hole where the ice used to be. And so these form these sort of wonderful little sort of rounded lakes called Kettle Lakes. We also have what we call eskers. And I've never managed to see one of these in real life. But the idea is, do you remember we said that the water under a glacier could be distributed, sort of pretty even across the base, or it could be flowing through channels. And this is what happens if you have water flowing through the channels, sort of melting away that ice around the channel, because all of the rock that was sort of within that ice near the channel and also being carried by the water is deposited. And so what you get is this sort of really funny line running through our landscape of sort of sediment deposited by this channel that was moving under the ice, which is, again, really fun. So we've moved relatively quickly, so I might let you go earlier today. If you can tell me which of these is not a glacial landscape. And then I have, I think, 2 more things to show you after this. So any last votes? Okay, let's take a look. Not going yet. Turn to the people behind you, turn to the people next to you. At least we have 2 options. Okay, last few votes. Okay, so we'll see how people did, and then we'll take 2 more minutes. Just give me 2 more minutes, and then you can go. Okay, so that's better, but still not great. What is B? It's a fjord, okay? And so you can see, what can you tell? You can see it's really steep-sided. It has even like a little hanging valley with a waterfall coming down. Don't, shush. 2 more minutes, please, guys. Shh. So A is obviously a glacial valley. It has these really steep sides, and it's a very wide, flat base. C, what is C? It's a cirque and a tarn. Okay, so D, what tells you that D is not a glacial valley? It's V-shaped, so it's a river valley rather than ice, okay? So the idea is, do you remember we talked about the fact that we can get these sort of big lakes forming in front of our ice? When our big ice sheet melted back across the US, we got an enormous lake forming. I mean, these are the Great Lakes down here. You can see that this lake was huge. And the really cool thing about this lake is it catastrophically drained really quickly through and into sort of that North Atlantic. And so what do you think happened if it catastrophically dumped all this fresh water into the North Atlantic? Change the salinity, and what would that have done? What movie was this based on? The Day After Tomorrow. So this is our Day After Tomorrow scenario. This lake catastrophically dumping fresh water into the North Atlantic caused a shutdown of the thermohaline circulation for quite some time. Okay? So one very last thing, which is that we talked about what happened on land, but there's one really distinctive thing that we can find if there are icebergs and ice in our oceans, and that is drop stones. You can see an example here. But the sediment making up our ocean floor is usually really fine. You don't see big sort of chunks of rock out in the open ocean. But when we have icebergs floating out and gradually melting, then they still carry big chunks of rock. And you can even see here where the sediment underneath was compressed as that block fell down and into it. Okay? So glacial landscapes, hopefully you enjoyed that. Well, I'll see you on Friday for ice cores.